Alright, this is going to be a short video over something called angular momentum. So most of the things that we have talked about so far, we've been able to go back and forth between translational and rotational or angular kind of motion. You know, we started off with kinematics, right? We have x equals VOT plus 1/2 AT squared. And that goes to an angular counterpart of omega. Let's do that in a different color. Okay, so we have theta equals omega naught t plus 1/2 alpha t squared. Okay, or we have this right here, force equals mass times acceleration, and in the rotational counterpart we have torque equals I times alpha. We can keep on going with this. We can say that kinetic energy, this is translational kinetic energy, was 1/2 mass times velocity squared, and then we could do rotational kinetic energy, which was 1/2 I omega squared, which we didn't really do much with that formula because we figured out that we could do rotational energy by just figuring out what the energy was that was missing. That was the lab that we did, where we got anywhere between 20 to 55% or so of rotational kinetic energy. So the idea is then we should be able to do the same thing with momentum. So momentum is mass times velocity. So what would the rotational counterpart be? Well, mass is, we can see back from over here, anytime we had a mass, we replaced it with the same thing, and that same thing was I. So mass is just regular inertia, so in this case it would be rotational inertia. And then back over here, anytime we saw a V, so there's a VO, and there's a V down here, so anytime we had a velocity, we replaced it with an angular velocity, or omega. So we don't use the same letter for angular momentum. Since we're doing random letters here in momentum, might as well do another random letter here, and it's a capital letter L. Capital letter L. And that is angular momentum. So if we're talking about units here, if you remember, I is mass times distance squared, so it's a kilogram meters squared. And then we have our omega here, which is technically radians per second, but we don't really write the radians. It's kind of a made-up unit. So if we compare that to what we have for regular momentum, it's kilogram meter per second, and then angular momentum is a kilogram meter squared per second. So it's basically the same unit, it just has this extra meter in there. Kind of way back over here where we had force is Newton and torque is Newton meter. So kind of the same thing. We have to deal with that distance issue here. So angular momentum behaves exactly the same as regular momentum. It's just saying that you could have something like, I don't know if you know what a lazy Susan is, but some kind of rotating cylinder sitting on a table, and as long as it's rotating and not moving, would we say it still has momentum? Well, the answer to that would be yes, it has momentum. It's just not going anywhere, so it doesn't really have a translational velocity, but it does have a rotational velocity, so we would say it has momentum. And just like how momentum is conserved for regular linear momentum, so we had those cars and we were crashing cars for the last couple of days, we know that if you crash two cars together that have the same mass, they double mass if they happen to stick together, so it's inelastic collision. So that would be saying, hey, we have a mass of 1 kilogram and another mass of 1 kilogram, and if they collide and move off together, now it's 2 kilograms, so you end up with a halving of the velocity. There we go, v over 2. And that was assuming that one of these was not moving. So we saw this in class a couple of times. So double the mass, half the velocity. Same thing is going to be true for angular momentum. So if you have this rotating cylinder here, okay, it's rotating this way with an omega of, let's say, 8 radians per second, and you plop down another mass sitting on top of this, and let's go ahead and make it a cylinder. That way we can easily see that it is rotating. So if we say that initially we had 1 kilogram here, and then we say we have 2, actually make it easier on ourselves, let's say 3 kilograms here, and this plops down, and it's not as easy as just doing the mass. We have to make sure that the I is similar, so let's make it the same radius. So we have 1 kilogram here, and we have 3 kilograms here. So if we have the same radius, all we're doing is basically multiplying the mass by 4 when it comes together. So we had 1 that was moving, and now we have 4 that's moving. So our velocity, our angular velocity, would then move to, since we're doing 4 times as much, it becomes a fourth of that, so 2 radians per second. So it conserves. We have conservation of angular momentum, just like what we do for regular momentum. Now, some of the weird places that conservation of angular momentum occurs is if you've ever watched ice skaters. So I'm going to butcher my ice skating drawing here. Here we go. Here's a person who's ice skating. So they're up on their toes, right? These are the ice skates. Okay, and they may have their arms out like this, and they're twirling around. I'm going to put the twirl in a different color. So they're twirling around like this, and they have their arms out. And then sometime later, they pull their arms in. So we have our ice skater here with our arms pulled in. You know, they cross over like that. And then we know that all of a sudden this ice skater spins much, much faster. Well, this is conservation of angular momentum. If angular momentum is I times omega, then what does pulling in the arms do? Well, it actually decreases the I, because I is kilograms meters squared, so we've decreased that distance part. And if we decrease the I, then the omega is going to have to go up along with it in order to keep this number constant, whatever that number is. And as far as the AP test is concerned, that's basically all we really have to know about angular momentum, is that it's like regular momentum. It's this inertia of something that is spinning. And if you were to increase I, then omega is going to go down, and vice versa. If you increase omega, then I would have to go down. But that's usually harder to do. You don't really mess with the I value unless you're talking about a human being that can move extremities around. But this is what we're talking about here, conservation of angular momentum. So I'll just have a few basic questions to follow this video, and we'll pick this up in the edX modules that you'll have to do next.